Overfitting is what happens when a model stops learning the relationship and starts learning the dataset. Today, we make that idea visible, not with warnings, not with slogans, but by watching a curve bend itself around noisy points and seeing how that bending shows up as geometry in parameter space. Here is the core problem. You only ever see a finite set of samples, but you care about the unseen points between them and beyond them. So the real question is not, can I fit these dots? The real question is, which fit will keep being right when the next dot arrives? Let's build a picture you can predict with. Imagine every model class as a set of possible curves. A line is a tiny set. Quadratics are a bigger set. Higher degree polynomials are enormous. Overfitting is not a moral failure. It's what happens when your set of possible curves becomes so flexible that it can match noise, not just signal. Now watch it happen. Same dataset, different model families. The line can't chase every point, so it compromises. A moderate curve follows the overall trend, but a very flexible polynomial can snake through every single dot. Training error becomes tiny, even zero, and yet the curve between dots starts doing acrobatics that nobody asked for. To make this concrete, we need two kinds of error. Training error is how wrong you are on the dots you already saw. Test error is how wrong you are on fresh dots from the same process. Overfitting is the gap opening up. Training error keeps going down, while test error turns around and climbs. But why does flexibility create this? Geometry. Picture the space of all possible datasets you could have gotten. Your training set is one point in that huge space. A flexible model can contort to hit that one point perfectly, but tiny changes in the dataset push the best fitting parameters far away. Overfitting is sensitivity. Small data changes cause big model changes. Let's connect this to what we already built in episode 4, gradient descent. Training is a walk downhill on a lost landscape. With a very flexible model, the landscape often has narrow ravines. You can reach a low training loss, but the bottom is needle minus, like move slightly and you climb a lot. That needle shape is another face of overfitting. Here's a numeric example, step by step, with no magic. We fit polynomials to the same 10 points. Degree 1 has 2 parameters. Degree 9 has 10 parameters. With 10 parameters and 10 points, you can usually hit zero training error exactly. But that doesn't mean you discovered the rule. It means you found one curve that passes through the dots. Let's actually show the math object we're optimizing. For polynomial regression, the prediction is a weighted sum of powers of x. The loss is the average squared difference between predictions and observed y values. When degree is high, there are many directions in parameter space that can reduce training loss, including directions that create violent wiggles between data points. Now the key geometric intuition. Training points constrain the curve only at those x locations. Between them, the curve is free to do almost anything unless you restrict it. Overfitting is the curve spending that freedom to chase random fluctuations. So the fix will also be geometric. Add a preference for simpler shapes or gather more constraints by collecting more data. Digression, but an important one. Overfitting is not just about model size. You can overfit with a line if your dataset is tiny and noisy, and you can avoid overfitting with a huge model if you have enormous data or strong geometric constraints. The real knob is effective flexibility, how many distinct shapes your training procedure can actually settle on. Holistically, here's where we are in the series. We invented models, then loss, then gradient descent as a way to search parameters. Overfitting is the first time we notice that minimizing training loss is not the same as solving the real problem. That gap forces the next invention, a way to reason about the trade-off between simplicity and flexibility. Recompression in one sentence. Overfitting is when your model uses its freedom to match the accidents of the sample, making it sensitive to tiny data changes and unreliable on new points. Next episode, we quantify that sensitivity with a clean visual split. Error from being too rigid versus error from being too twitchy.